This is the first of the modules which is devoted to the analysis of count data. Now, textbooks often tend to spend a lot of time on binary outcomes and binomial outcomes and the logistic and probit model. Another class of discrete data which is by no means less important is the count data. You have seen the basic model for count data, which is the Poisson distribution. In a previous module where we had discussed the kinds of data which might arise for generalized linear models, we had seen several variants of this. We had seen situations where there could be rates rather than counts. We have also seen cases where the classical assumption that the mean and the variance are identical do not hold for a series of counts. In this module and the next module, we are going to talk about several different models for count data. The learning objectives for this module. Firstly, we will quickly recap what kind of count data types might arise in regression settings. We shall define the Poisson regression applied to the raw counts. We shall define a variant of Poisson regression, which is called negative binomial regression. And finally, we shall define another variant called the Poisson regression for rates. So this is the first of the modules which is devoted to analysis of count type data. Let us look at some examples of counts. On the first line on the slide, you see the very popular Poisson distribution, which is usually used to model counts of some kind of event happening over time or over space. So there are three examples of counts. It could be the number of species of turtle. So there is a Gala data set in R, for example, which looks at the number of species of turtle on the various islands of the Galapagos. It could be the number of seizures which a patient on a particular medicine experiences over time. It could be the number of accidents occurring over a city. Now, sometimes we don't see the counts directly, but we see a transform of the counts called rates. So, for example, the incidence rate of lung cancer, say per 100,000 population, the mortality and morbidity rate of a specific population, the fertility rate. We could look at the number of accidents per capita. We could also look at the number of earthquakes per capita. In each case, the per capita division is made to make this comparable across, say, larger and smaller countries. I have mentioned something called overdispersed counts in various models. Now, we all know that for the Poisson distribution, the mean is equal to the variance, and so if the Poisson distribution is a good fit, we would expect the mean and variance to be similar. There is, of course, no requirement that the mean and variance must always be identical when we have count data, and in this and subsequent modules, we will see some examples of why they may not be equal. So this is an example which is based on an R illustration for count data where the variance y is not equal to E of y, but rather variance of y is equal to some factor phi multiplied by expectation of y, and the circle part of the code says that the dispersion parameter for the Poisson family is taken to 31.749. So phi is equal to 31.749. Now, we all know that the Poisson family has no extra dispersion parameter, so this is rather puzzling. We shall revisit this in a subsequent module. This is just to give you an idea of the various types of counts which might occur in regression settings. The most popular and common kind of count data, of course, arises from a contingency table. So here is an example of contingency table where we have looked at two factors. which is the highest degree which a person might have received, classified as less than high school or junior college, bachelor or graduate, and the person's religious belief, fundamentalist, moderate, liberal. The resulting classification is commonly referred to as a contingency table. You know, the multinomial data is the natural model for this kind of a table, and we shall see in this or in the next module the connection between the Poisson regression and multinomial data. There are, of course, more subtle points in this. For example, you will observe that the highest degree is actually something which can be referred to as an ordinal variable, whereas religious belief is a nominal variable. In earlier modules, we have defined the various kinds of analysis and summary measures which are appropriate for the settings where we have ordinal data or nominal data. For now, we shall concentrate more on regression methods. So the most common Poisson regression model is the Poisson regression with a log link. This is also called the log linear model. So the log linear model simply says that log of mu is equal to alpha plus beta x. Or put in a different way, that mu is equal to e to the power alpha plus beta x, or e to the power alpha into e to the power beta times x. Why is this important? For two reasons. First, observe that the log linear model is the canonical model for the Poisson family. And secondly, observe from the equation given on this slide that a unit increase in the covariate has a multiplicative effect. So, if x is changed into x plus 1, mu is equal to e to the power alpha into e to the power beta to the power x plus 1, which is mu corresponding to the value of x multiplied by a factor e to the power beta. So increasing a covariate by a unit amount, keeping all other covariates constant, will have a multiplicative rather than an additive effect on the mean. Let us look at a data set on horseshoe crab mating, which has been discussed by Agresti in his book. The count data which I am concerned with here is the number of satellites of a female crab. By number of satellites, we mean the number of male crabs which reside near a female crab. We're interested in relating this number of satellites to covariates of the female crab, which are color, spine condition, carpus width, and weight. For now, we shall only consider width as a predictor, though of course it is easy to generalize the models which we shall define to include additional covariates. So this is a snapshot of the complete data set. The columns give the various covariates. So C, for example, stands for color, coded as light medium, medium, dark medium, or dark. S is the spine condition, where 1 denotes both good, 2 denotes one worn or broken, 3 denotes both worn or broken. W is the carpus width measured in centimeter. WT is the weight measured in kg, and SA is the number of satellites. The original source for this data set is from Brockman of the University of Florida and described in the journal Etiology, but it has also been discussed in detail in the 2002 book by Agresti. Now, a good exercise for any regression model fitting is to first make a rough plot of the data. So here, for example, we see a scatter plot of the number of satellites as a function of the width taken on the x-axis. Unfortunately, however, the plot is not really that helpful as it would have been for the case where we have a continuous outcome. The reason, as you know, is that count data is heteroscedastic and there is so much variation in the data that although we get some suggestion of a generally increasing trend, the plot is not as useful as it would be for the case of a continuous outcome. We could perhaps get a more revealing plot by classifying width into several categories and then plotting the category means against the width and smoothing the plot. This, of course, requires a reasonably large data set. GLN software was used to fit the log linear model to the data. The log linear model, the fitted regression equation, says log of mu hat equal to alpha hat plus beta hat x. We can get the maximum likelihood estimators of alpha and beta, and it turns out to be alpha hat equal to minus 3.305 and beta hat equal to 0.164. We can use this to plot the regression line from this fit. We can, of course, also get the corresponding standard errors of alpha hat and beta hat and use them to test the significance of the coefficients. For purpose of comparison, we have also fitted a linear model to the data. So a linear model is, as usual, mu hat equal to alpha hat plus beta hat x, and plugging in the maximum likelihood estimators of alpha hat and beta hat, this is equal to minus 11.53 plus 0.55x. This shows a plot of the two regression lines superimposed on the original data. So the somewhat curved hyperbolic plot corresponds to the log link, and the straight line corresponds to the identity link. Now, of course, the two plots are not identical, although it might be argued that they are close for the greater part of the range of the data, which is towards the middle. At the two extremes, of course, they vary, and thus, if we are interested in plotting at the extremes, it is a good idea to use the log link rather than the identity link. In several motivating examples towards the beginning of this paper, we have discussed why the use of identity links is not really desirable for the situation where we have count data or binomial data. So for this example also you see that if the main focus is on prediction towards the extremities of the range, it is important to use the log link rather than the identity link. Now, count data, as I have said earlier, can often show greater variability than the Poisson distribution allows for. For the horseshoe data, for example, if we group the data by width and we look at the corresponding means and variances, we will see that the variances are much larger than the means in each category. So this suggests that the Poisson distribution is not necessarily identical, and in fact this is a consideration which we shall revisit in a later module as overdispersion. Now the cause for overdispersion here is subject heterogeneity. So for example, note that we have only used a single covariate, which is width, to predict the number of satellites. If the reality is that the number of satellites also depends on weight, color, spine condition, for example, then the data will see greater variability than can be predicted by width alone. Thus, we have fitted an alternative to the data, which is called negative binomial regression. The negative binomial distribution has probability mass function f of y given k and mu equal to gamma of y plus k by gamma k gamma y plus 1 into k by mu plus k to the power k into 1 minus k over mu plus k to the power y for y equal to 0, 1, 2, etc. K and mu are the two parameters. Now for this distribution, expectation of y is mu and variance of y is mu plus mu hat square by k. The index k is called a dispersion parameter. As k inverse tends to 0, variance of y tends to mu, and so the negative binomial distribution will converge to the Poisson. But in general, the presence of k allows it to model the situation of overdispersion. So this has been fitted to the data, and because the estimated variance is roughly mu hat plus mu hat square, as k inverse turns out to be 0.98, this allows for larger variance than the Poisson GLM. We can compare the deviance values for the two models and see that the negative binomial distribution gives a better fit. Now, in my introduction, I mentioned situations where we do not observe counts directly, but rather we observe them in the form of rates. Now, when we have a particular event occurring over time or space or some other index of size, it is often relevant to standardize them by this measure of size and to get a comparable measure called the rate. So this leads to a log linear model, but with something called an offset. So say, for example, that the measure of size is given by a variable ti. Then, instead of saying log of mu y equal to alpha plus beta xi for the log linear model, we now say log of mu y by ti is equal to alpha plus beta xi. This can be expressed as log of mu y minus log of ti equal to alpha plus beta xi, or log of mu y equal to log of ti plus alpha plus beta xi. So the term log of ti is something which occurs in the regression equation, but it does not have an unknown coefficient. Such a term occurring in a regression is called an offset. So Poisson regression for rates is essentially the log linear model, but it contains an offset. For the identity link, this would reduce to mu of ti equal to alpha plus beta xi, but this is not a problem because this is equivalently written as mu y equal to alpha ti plus beta xi ti. So the effect it has on the model is to remove the intercept but introduce another covariate ti and transform the covariate xi into a covariate xi ti. This can be handled simply. I leave it as an exercise to you to consider how the iteratively reweighted least squares equations would change for the Poisson regression in the situation where we introduce an offset. Here is an example for Poisson rate regression. The data is taken from a 1981 paper by Laird and Olivia, who analyzed patient survival after heart valve replacement. So they looked at 109 patients and classified them by the type of heart valve, aortic or mitral, and by age, which is less than 55 or above 55. So the patients were followed up until they either died or the study ended. Operations occurred throughout the study period, and follow-up observation time ranged from 3 to 97 months. So in this table, we see the number of deaths during the follow-up period by valve type and age. So this is that first layer of a three-way contingency table that classifies valve type, age, and whether or not the person died. Now note that it is not appropriate to analyze the 2 by 2 by 2 table using a binary GLM because for the probability of death, because the subjects had different risk times. So it would not, for example, be meaningful to treat a subject who was observed for 3 months only and a subject who was observed for 97 months as identical. So to make them identical, we are going to standardize by this measure of size, which in this case turns out to be duration of follow-up. This is typically denoted in the literature as the time of risk. So here are the results from fitting this model. Log of mu ij over Tij, where Tij is the time of follow-up, equal to alpha plus beta 1 Ai plus beta 2 Vj, these being the two covariates, age and valve type. A is of course a dummy variable, 0 and 1, 0 for the younger age group and 1 for the older age group. And V is a dummy variable for valve type with V0 for aortic and 1 for mitral. We can define Nij as the number of deaths for age Ai and valve type Vj. Assume its expected value to be mu ij. For total time at risk, Tij. So given Tij, the expected rate is mu ij by Tij, and the model is log of mu I by Tij equal to alpha plus beta 1 Ai plus beta 2 Vj. So we can then use the standard maximum likelihood techniques, treating the Nij as my outcomes and Ai and Vj as the covariates, Tij as an offset. Doing this, the maximum likelihood estimates are given by beta 1 hat equal to 1.221, beta 2 hat equal to minus 0.330. The corresponding standard errors, also obtained by maximum likelihood from the information matrix, are 0.514 for beta 1 hat and 0.438 for beta 2 hat. We can use this to construct wall type tests and confidence intervals. We can see that given the valve type, the estimated rate for the older age group is e to the power 1.221, which is 3.4 times that for the younger age group. We can also obtain the corresponding goodness of fit statistics, which is the chi-squared. And we can see that if we drop the valve effect, the model fits nearly as well. And if we drop age, the model no longer fits. To summarize then, count data is another important class of data for which generalized linear models can be applied. Counts could be just that, basically count of an event occurring over time or over space, or a count which we wish to relate to one or more covariates. In such a situation, we use something called Poisson regression. Of course, we could have multiple links. The most common is the log linear model. We have seen the details of this in this module. Another situation is where we observe counts, but there is some implicit denominator by which the counts need to be divided to make them comparable. So, for example, they could be reduced to the number of counts of an event occurring per unit space or per unit time or per unit population. We have seen some examples of this, and in this case it is necessary to build a Poisson regression model for rates. We can do this by specifying something called an offset. Now this is slightly more complicated than it would be for including an offset in a linear regression. There are many other variants of counts, such as overdispersed counts. We have briefly seen this in this module, where we have used the negative binomial distribution as a solution for modeling count data where the mean and variance are not necessarily identical. In subsequent models, we will consider more refined techniques for modeling counts where the mean and variances are not necessarily equal. This is a well-known phenomenon called overdispersion, and the technique which is best known for handling this is called quasi-likelihood. We will also define something called a zip model, which is relevant to counts with an excessive number of zeros.